Manitoba and holds a portion of the 2015 Breakthrough Prize in Fundamental Physics for the discovery of neutrino oscillations. His current research is a follow-up on the Nobel Prize-winning work of Dr. Art MacDonald for the Sudbury Neutrino Observatory work to resolve the solar neutrino problem. Dr. Jamieson is a leader of the photogrammetry package of the Hypercameo-Gandhi collaboration, which involves 600 researchers from 22 countries. Dr. Jamieson is also a leader in data science techniques for experimental particle physics, and his work has been published in academic data science journals such as Big Data. Please welcome him. Next we have Dr. Juliette Mammei. She's an international leader in subatomic particle research, advancing knowledge in nuclear and nucleon structure, and testing critical theories of the standard model of particles and interactions. She's widely recognized in the field of parity violating electron scattering, and currently Dr. Mammei is working on a major experiment which intends to measure the weak charge of the electron 5 times more precisely than previously achieved. She is dedicated to improving First Nations student outcomes and is an advocate for nuclear physics education and equity, diversity, and inclusion within Canada. In 2024, Dr. Mammei was elected to the Royal Society of Canada, one of the country's highest academic honors. Please give a round of applause. Then we also have Dr. Jayanne English. She's a Canadian astronomer whose research concerns galaxy formation and evolution, galaxy mergers, intergalactic gas clouds, and polar ring galaxies. She's also known as a science communicator for her work in scientific visualization and in particular in the use of color in images of galaxies. Her work at NASA involved the Hubble Heritage Project, through which she connected her earlier art education with astronomy in the production of astronomy outreach images. English was the 2021 recipient of the KELAC Award for Astronomy Communications of the Canadian Astronomical Society for her work building a unique outreach program that bridges art and science. She was named to the Order of Canada in 2023, honored for her innovative work at the crossroads of science and art, and for making astronomy accessible to all. Please. Then we have a PhD student, Jayanne Na. Jayanne is a PhD student at the University of Manitoba and has been part of the Bell 2 experiment since being an undergrad intern back in Korea. Jayanne stepped into the field of particle physics not just because of theory, but more for the scale of it all, like a massive machine built with cutting-edge technology and a global corporate type community working together to explore the unknown. It inspired her enough to become her vision for a career. During her internship and master, she had the chance to work across many parts of the experiment, from simulation, software, computing infrastructure, such as computer management, and finally the precision studies of standard model. Through that process, she realized that she wanted to actively be involved in searching for new physics beyond the standard model. She's in the 3rd year of her PhD program now, and has been leading a search for a new particle called the dark photon. So that's all she's done. And finally, but not least, we have Arina Seragotin. She's an undergraduate student of physics and astronomy in a co-op team with a specialization in astrophysics. She has had internships working with 2 particle accelerator collaborations at the University of Manitoba, Bell 2 and the Muller experiment. This past summer, she held a co-op term with the RAMS experiment at Snow Lab to search for rare decay searches of the radioactive element lutetium-176. She also engaged extensively in outreach. She is the communications director in the Organization for Physics Undergraduate Students, OPUS, and a member for Women Plus in Allen. And she has been a frequent volunteer at Lockhart Planetarium for most of her undergraduate career, helping a variety of students from urban schools and amateur astronomers to learn more about the night sky. She's currently doing her undergraduate thesis with Dr. Tyrone Woods, where she looks further into unique nebulae that lack the hot young stars responsible for ionizing them and are emitting strong hell lines. Currently, she's working at the Makerspace, a student-led fabrication shop that hosts an array of 3D printers and CNC machining, which helps print part for the Molly. Now that we have gotten to know them, let's hear them out. Dr. English, could you please tell us where do you see the intersection between physics and art?
So, you can, okay, great. Now you're at a very special time in your education where we're talking about transdisciplinarity instead of interdisciplinarity. So that is where you get to put together various different disciplines together. So interdisciplinarity is when we work with each other, like an astronomer with a particle physicist, right? But transdisciplinarity is when you bring the things together yourself, the different disciplines, or you have big teams that span from the humanities right through to physics. So we're designing projects now where we have social scientists embedded in our group, choreographers and kinesiologists, so we're including the medical aspects of how we work together and trying to change the culture of science. So that's one of the places, right? And for myself, I've been told that when I'm doing my work, I don't distinguish between art and science. So visualization, scientific visualization, is kind of like computer science was back in the 70s, where it's becoming a very important element for how we analyze our physics. When I was talking to the director, I should tell you that the director and I had a great conversation. He told me to focus on the fact that I've actually been down into Snow Lab before they filled it with water. And we were both actually worried that I would re-experience my claustrophobia going down in the cave for 5 minutes. The cage that takes you down. It was a terrible experience. But being down there otherwise was wonderful, and it's actually really quite warm in the tunnels. It was very interesting. And of course, we got to go into the big space before it was had all its detectors and so on. And so we talked a bit about art and science, but mainly about like the differences. And I think we've just all experienced a gallery view of landscapes and still lifes, but they were based on physics instead of flowers, right? So I found that very beautiful that we got to sit there and look at these images of architecture and spaces and sit with those images for a while as if they were paintings. He said that what he was doing was using metaphor, images, and sound to point out to people the beauty and the ambitions of the physicists, like the beauty of their experiments and the ambitions of the physicists themselves. I don't know how long you want me to talk, so I'll pass it up.
Thank you. That was really interesting. Thanks. But yeah, we need to move on, sorry. Dr. Jamieson, could you please tell us a little bit more about why neutrinos are such an interesting particle to study and what makes them so unique?
Sure, I can do that. So yeah, this whole movie was about neutrino detectors. I don't know how many of you have even done a particle physics course and know what a neutrino is. It's probably a very mysterious thing. It's a particle that was invented to try to explain something in the 1930s. When they were doing nuclear physics experiments, they discovered beta decay. So if you have some nuclei, they decay, and you get electrons out from these decays. You can study those. And they measured the energy spectrum of these and found out, wait a sec, there's a bunch of energy missing from the nucleus when this happens. And it's like a very fundamental thing in physics that you gotta have energy conservation, or that's like one of the fundamental things. If you don't have that, then it's broken. So where did this energy go? And it's a very bold idea to come up with the idea that, well, maybe this energy is carried away by some particle that has no mass, has no charge, and we'll call it a neutrino. No one's ever going to see it because it's so weakly interacting. But in the 1930s, people actually made experiments big enough to see these by putting big detectors near reactors where there's lots of decays happening. So it's a very interesting particle because it's very hard to detect. And then when we were detecting it, we realized, well, there's other things we can detect naturally. So lots of them are made in the sun. We can try to measure those. And so people made big detectors to try to look for neutrinos from the sun. And they saw them, but then theorists tried to calculate how many neutrinos should we see from the sun. And they found out that we were only seeing about a third of the neutrinos predicted. It was like 20 years of experiments going on, different experiments, measured the exact same thing. Theorists tried to improve their calculations, and still this discrepancy persisted. And it wasn't until the late 1990s when Super Cameo Candé measured a different kind of neutrino called atmospheric neutrinos. So cosmic rays coming in from space come in and hit the upper atmosphere and make something called a muon neutrino. And measuring those, we found there was a deficit of those coming from the other side of the Earth. And there's a theory called neutrino oscillation, which is a quantum phenomenon that neutrinos can change their flavor as they travel through space. And so this became kind of a predominant theory. We've now measured it again with T2K experiment, and seeing that if we start with particular flavors, it travels along, it changes from one flavor to another. A quantum mechanical process. So it's a very interesting particle. It's had a lot of measurements.
Yes, it certainly is. We really got to. Well, I got really excited about seeing this. So yeah, thank you. Dr. Mammei, could you please tell us a little bit about the broader goals of astroparticle physics and how does the study of neutrinos? Oh no, sorry. No, yeah. How does the study of neutrinos fit into this?
So I might be the least qualified to talk about the broader. I'm not an astrophysicist at all. I'm a particle physicist, but so you're getting my sort of outside perspective. So for me, besides using neutrinos to study astrophysical objects and supernovae and black holes and things like that, it's to look for physics beyond the standard model, which you've heard a few times mentioned. So what that means is we have a standard model of particles and interactions, and all that does is summarize our knowledge of the fundamental particles that exist and the forces that mediate how they interact with each other. So you may have heard of electrons, protons, and neutrons, but protons and neutrons aren't fundamental particles. They're actually made of something called quarks. And so there's electrons, muons, tauons, they all have neutrinos associated with them, and then there's up, down, strange, charm, and top and bottom quarks. And they're antiparticles. And then that's what we believe the universe is made of, except there's evidence that there's things missing. One of the big questions that was mentioned was, why is the universe all mostly matter? Because there are antimatter particles, and when matter particles coincide with antimatter, they annihilate each other. So there's an imbalance. There's more matter than antimatter, otherwise we wouldn't exist. And so for me, one of the biggest questions are to answer what is any physics beyond the standard model? Are there dark matter particles? Is there a force that we haven't discovered yet? Things like that.
Thank you very much. Alina, could you please tell us about a little bit about the environment? How is it like at SNOLAB?
Thank you. So SNOLAB was a little bit different from how, can you hear me by the way, like it works? SNOLAB was a little bit more different than how they portrayed it. I understand that they were trying to make it a little bit more tense, but once you started going to SNOLAB every day, I worked at SNOLAB over the summer for 4 months, and so half the time I would be underground, and the other half of the time I would be above ground. So Snow Lab has both an underground lab and also an above ground lab. And I think they really tried to make it look more tense and kind of isolated, when in contrast, Snow Lab is actually like really fun. I remember one of the best memories was I actually got to, like, they brought a bouncy castle to the mine site, and I got to race my supervisor, and I won. So I think that was like really fun. And even when you go underground, usually when they stuff you into the cage, yeah, they try to shove in as much people as possible, because Snow Lab gets very limited elevators to go up and down. But they managed to cram about 80 people into there. So underground, on the typical day, you'd have about 80 people in there. And you'd also have scientists working above ground, as well as technicians and people who actually maintain the lab to make sure that it stays clean. Overall, I think Snow Lab was a great experience, and I definitely recommend, even if you get to visit it for a single day, you get to learn so much that they don't necessarily show in an institute. And I do want to say that Snow Plus is just a very little, I mean, obviously it's kind of the face front of Snow Lab, but there's so many other experiments that Snow Lab is doing as well, like Super CDMS and Q, they're looking into dark matter, and I definitely recommend looking into those experiments. I personally worked with a smaller experiment called RAMS, and that stands for Radioactive Measurement Project at Snow Lab. And it was just me working with it during the summer. But Snow Lab was really good at kind of making it a community. It's also the people that just make it sometimes. I got really lucky. I had an amazing supervisor, Max Stuckel. I guess positive reviews to him. And I also got to meet a bunch of other undergraduate students, mainly from the GTA, but it was just phenomenal meeting other students like from the University of Toronto or Waterloo or McMaster, because then you get to kind of see the different perspective, and you get to see other niche subjects that they study that you kind of get, like, you kind of get to know everybody at the U of M. So it was really nice to see that. I also just wanted to add that with going around those experiments, in contrast to a university type of setting, you can kind of get introduced to all of the experiments. Similarly to IceCube, there's also another experiment that they have called HALO, which also looks into identifying supernovas prior to their explosions. So it was also really interesting to see a bunch of other experiments and kind of get to know them, as well as the people behind those experiments.
Thank you, that was very enlightening. Could you please tell us a little bit about what the day, the life of a particle physicist is like?
The life of the particle physicist?
Yeah,
Am I a physicist? Yeah. Okay, so here's a disclaimer that what I do is quite different from what she does. So I'm working with a particle collider, and what I do in daily basis is just like data analysis collected by the detector that something like she built, something like that. So in other words, what I do all day is just sitting in front of my laptop doing the data analysis. So my ultimate goal is to find a signal from the dark to kind of like something like dark matter thing from the collected data in the colliders thing. So going to the point, my day starts with going to the gym because I sit in front of my laptop all day long. So I need to go to the gym to just like fit my daily active goal. And then I come to my office and I open my laptop and I start doing the data analysis. So for those people who are actually interested in going to this graduate school, especially in the particle physics, I highly recommend you to learn a little bit of like computer science, especially Python, yeah. Because the modern particle physics is more of the computer science, the data analysis, than the actual physics. So yeah, that's basically my day. I go to my office and I analyze data, and occasionally having a meeting with people all around the world. Yeah, that's good.
Thank you very much. Yeah, I can vouch for that. Okay, so we have 3 more questions, and then if anyone wants to ask them a question, there's 2 people with mics, and you can just raise your hand and
want to do it now or later?
Yeah, I think, is it, well, I will have the 3 questions first and then like the public is it. Thank you. Sorry. So, Dr. Mammei, can you please tell us a little bit about your work to make the astroparticle physics space more inclusive?
So, as I said, I'm mostly on the subatomic physics side, so that's okay. But I don't want to sound egotistical, but I think just being there is a way to help improve EDI. I'm on collaborations with hundreds of people, and there may be 3 or 4 women in the room. So being there and being visible for the younger students coming up, I think is really important. Another thing I do is every summer I host Indigenous high school students. They come to my lab and they do a bunch of physics experiments. They measure the charge and mass of an electron that week, and then they do cloud chambers that hopefully actually work. This helps expose the students who may be first generation college students. You know, they're hoping to be to the environment of the university and to get an idea of what it's like to do research. One thing that I'd like to do in the future is to reach out to far northern or rural communities. A lot of them don't even have physics classes, so I'd like to work to provide them with some exposure to physics when they're in high school so that they can have an idea if they would like to pursue that in college or university.
Thank you. Thank you so much. Somehow related, Dr. English, could you please tell us about how you make astroparticle physics accessible to the public? How to make this kind of research accessible to?
Yeah, sure. So personally what I do is I make outreach images to, it actually works for all of science, right? The images, because they're easy for, well, astronomy has great data that we can make images from. So I take the data and I assign colors to different energy ranges and make compositions, and I can get images out there that 1 million people see when it's launched on Astronomy Picture of the Day. One of the things about this movie that I'm impressed with the director doing is that he's gone into a subject that doesn't have a lot of images, right? And he's making it image-rich and interesting for the public. So his goal is to not do something didactic, but to do something more poetic, so that it appeals to people who wouldn't, like already physics people are interested in the physics, right? So this is meant to reach out to those that aren't yet interested in the physics. And what impresses him about the physicists, he thinks that you that want to do physics, you're really courageous because you're going to do experiments where you don't see the end product, but that it's generational experiments. And he wants to get people interested in caring about your experiments. So that's why this movie is very, I guess you would say, artsy, right?
Okay, it makes a lot of sense. Thank you. And finally, Dr. Jamieson. Yeah, more on the physics side again. Could you please tell us about what are the key aspects to focus on in the design of particle detector experiments of this scale?
Sure. So back to me, I get the physics questions. So remember the neutrino? It is very. It interacts so weakly, right? It's hard to see these things. And the statistic is that you have 1 million of them going through your thumb every second, but in your lifetime, in your body, only 2 of them will interact. The other analogy is, well, usually you try to stop radiation by stacking lead bricks to stop your radiation. If you wanted to try to stop a neutrino, you'd need a light year of lead bricks. So how do you detect something that's so ridiculously weakly interacting? So that's the design challenge of a neutrino detector. So there's two keys. One, lots of neutrinos. If you have lots and lots of neutrinos, one will interact. Second key is really, really big detector. So you have a big volume, you have more things to interact with. And so, like Super K, that's a 35-meter diameter detector. Next generation will be 70-meter diameter volume of water that we're looking at. So the big challenge is almost more of an engineering challenge of, can you build a big enough tank to hold your detector?
Yeah, they're pretty amazing. Thank you. So please, if anyone has a question, you're more than welcome to.
So I have a question for Dr. English. I was wondering about when you make your, I guess, the graphics to better understand the physics. Is that something that's geared more towards the public or more towards the researcher?
So, interestingly enough, when we started to make images for the public, the researchers insisted it goes in their professional publications. So unexpectedly, these images are actually discovery machines. So when I make them now, they're for both. I'm always making them both for discovery and for the public. So I'm folding in, so I use techniques from art and design, composition, how colors come forward and go back, and so on. But that also, the colors coming forward and go back, help you visualize your data and your discoveries, right? And explore your data. So it's now very transdisciplinary.
Thank you very much.
You're welcome.
There was and you mentioned how you can use the detectors to find out where there's going to be a supernova ahead of time. How much head notice do you get? I guess it's going to vary depending on how far away it is, but approximately.
Well, if the sun was going to go off, we'd get it, the neutrinos 8 minutes before the sun goes off, right? So, yeah, it depends on the distance, right? But it's certainly, they're traveling, yeah, that's a very good question. I think what happened with, well, I do remember a story, this is going back to the 80s, so just don't hold it against me if I get it inaccurate. But when supernova 1987A went off, they could have detected the neutrinos if Super K was actually working, but everybody took the weekend off. So there would have been more of a triangulation to figure out where, where the neutrinos were coming from. So in that case, I believe it was only minutes before, but I can't remember exactly. But that's in a companion galaxy to the Milky Way.
I know Super K did detect neutrinos from 1987, but I guess they weren't there to do the triangulation. I didn't know that part of the story. Okay.
So one interesting thing is now we also have gravitational wave observatories, and this is way outside my wheelhouse because I'm a subatomic physicist. But we can actually, when I heard the title of the movie, it made me think of what people are saying now, which is that we have multi-messenger physics. So not only do we have optical and other wavelengths of light that are outside of our visible range, like X-ray and infrared, and we can detect neutrinos. We also have gravitational waves that we can detect. So I forget which one comes first. The neutrinos come first and then the gravitational waves. So we do get a little bit of advanced warning and we can look in a certain place.
Thank you very much. I think there's some other questions. Okay, yeah.
Well, thank you first for organizing this. I think it's so great to have this science
it for me was like more contemplative and informative at the same time. So I'll say here my question is like for all the panel, if you could describe briefly like the moment that you like most, where you get to see like art with the physics of the topic, which one would you choose? For example, for me, I will say that moment when they were showing the mountain, and then everything that was below, it was impressive. So my question is, which will be your, like the second that you like most about this? In the movie?
Maybe we can go like this.
Okay, so I really felt it's a good question because the director actually asked the question, what did you feel when you looked at the images? And so because I'm familiar with snow, both literally and snow lab, the thing for me was the Japanese scenes and actually going into the tunnel to go under the mountain, going from forest through into mountain, and then the human element that was there with the hanging things over the entranceway. And that shows like even though the spaces can be empty, there are humans there, and this is all designed and made by humans. And yeah, so I think going into the tunnel was something that I really enjoyed in the film.
There was a part, it was near the end, I think, where it was, I think, showing a neutrino coming from a distant black hole, and it was showing all these tracks. And it reminded me of the cloud chambers and what you would see in the cloud chambers. And I always knew I wanted to be a scientist. I think that's unusual, but ever since I was in high school, I knew I wanted to be a subatomic physicist. And I pictured seeing the photographic plates where they would actually have bubble chambers, and when the particles went through, they would make bubbles, not like the cloud chambers, but actual bubbles. And they would actually take pictures of them. And these women would actually measure with rulers the photographic plates. They would be backlit. And that scene reminded me of that. And made me a little sad because we don't do that anymore. We sit in front of computers and we analyze the digital signals that come. We don't get to see the evidence directly, well, sort of directly. And another thing I liked was when he was showing in the detectors, either in I guess he did it for all three, but he was showing the flashes of light. That's not really what we would see, right? So it's a little bit of artistic license, but that's how I sort of imagine things, even though that's not how it really happens.
So it's a tough question. I think for me, I just see like Super K is such a beautiful detector. Like just because it's covered, 40% of its surface area is covered with these photosensors that are able to see single photons, but each of those surfaces is so like reflective and shiny. It almost gives me nightmares of the physics part because we have to understand all these reflections and things to great accuracy. But I think the pictures are so beautiful because you can see kind of, if you look at just one photo tube, you can see reflected in it all of the rest of the detector. And then each of those is kind of like, almost like a recursive thing. You're seeing that reflection over reflection. And so I think it's kind of beautiful, artistically at least.
Can you pass it on, please?
Okay, so thank you for asking that question. That is so deep. So for me, I just like 100% agree with the professor. So my favorite part and what actually just like dragged me into the particle physics was that gigantic, massive detector. So I like the theory. The particle physics was my favorite kind of coursework when I was in the fourth year. But what actually made me to step into this field was that just straight up cutting edge technologies and the scale of that experiment. That was just so fascinating for me, and that is artistic, right? So yeah, that was it.
My favorite part, sorry, that's also a really good question. My favorite part of the visual was the shrines. Like, I liked when they showed all of the different shrines. I think there was something so human about it, even though it wasn't necessarily like the most pretty. It was kind of like really nice to see, because even though you still have all those detectors and it's so isolated, there's still like a human touch to it. So I really liked that. I also really liked it when they would, I mean, just in general, seeing Snow Lab just show up there, and like it's kind of eerie and weird to see to a place that you went there so frequently being shown as like, I don't know, like this kind of like ominous place. It was kind of really eerie and kind of nice to see it again in a way through like a photographer's eyes, I guess.
I'm sorry. No worries. Thank you. Yeah, I agree with you. We have a couple of more questions.
So my question is for anyone who cares to answer it. When I hear about these experiments, about these detectors, I think in my head, well, I hope your theory is proven and we come one step closer to solving science. I hear from other people, like on YouTube, scientists, science educators saying, I hope it's something completely unexpected and there's new science out there and something weird and more interesting for us to discover. Which of those two sides do you find yourself falling on more?
I think Dr. Jamieson wants to.
It's a great question, yeah. So I think in science we don't know the answer, right? That's part of the reason we're doing the experiment is we want to see what's out there and try to understand it better. And I think one of the great examples of this is Super Kamiokande. The name Kamiokande comes from the mountain is Kamioka. It was going to be a nucleon decay experiment. So their whole experiment was they want to see, do protons decay? So the crazy thing. But now it's known best as being a neutrino experiment. Why? Because what they saw was neutrinos, because the decay didn't happen, at least not at the level they could see, but they could see neutrinos, and so they measured neutrinos really well. And so it's kind of a discovery. You know this is going to happen. Kind of they're just studying this background, and that's how they came up with this whole thing. That one of the grad students, Kajida-san, was given the problem of, well, okay, you study the muon neutrino background for our nucleon decay. And he found, oh, we're missing a bunch from the downward direction. It's almost by accident, kind of, that this oscillation was discovered.
Some experiments are designed to look for a particular model, from a particular model. The big experiment I'm working on is trying to measure something that is very precisely predicted by the standard model, and we're looking for a deviation from that. So we're looking for something that would surprise us, that would tell us that, okay, if we measure this so very precisely and it doesn't agree with the standard model, there's got to be something else out there.
So doing science is a process and it's counterintuitive. You don't know what it's going to be. It's not going to be what your intuition is. So it doesn't matter how you set it up. You don't need to be on one side or the other. So you can set it up one way and you have a win-win situation. If it shows what the model was predicting, you learned that. And if it shows the opposite, you haven't lost. You've learned something new. So it's win-win. So you don't have to pick a side.
Thank you very much. Okay, we have another question.
So my question is, after the neutrinos are detected, what sorts of experiments are designed to understand the different kind of interactions, or whatever questions we are looking forward to answer?
So you want to know, I guess, why are we still measuring neutrinos? We already found this weird neutrino oscillation. What's next? Is that kind of the question? Yeah, okay. Right, so I guess, why is Hyperkamiokande being built? It's a massive investment to try to do this. And what would we want to learn that's different than before? Well, it turns out we actually also have beams of neutrinos, so we won't talk about those, right? So there's actually, we're able to make a beam of neutrinos. So a very high intensity beam of protons hits a target, makes a bunch of particles, but one of them is a neutrino. We can actually, by focusing some of the charged particles, we can kind of aim our beam of neutrinos. So on one side of Japan, we make this beam of neutrinos, and on the other side, it actually aims at Super Kamiokande. We see those neutrinos in Super K. And we see them oscillate. So what's next? So we can also, just by changing the sign of our magnets, we can, instead of focusing neutrinos towards Super Kamiokande, we can focus an antineutrino towards Super Kamiokande. So, okay. If you've watched Star Trek, you've seen antiparticles. They are real, and apparently, if a neutrino has an antineutrino, then we'll be able to see, do neutrinos and antineutrinos oscillate the same or not? We don't know the answer to that.
You get one.
Yeah, go ahead.
So this question is for anybody who's been to Snow Lab or any of the other facilities. We saw in the film the level of intent there is in keeping these facilities clean, whether that be through ventilation, with high cycles, washing stations. Now, despite these preventative measures, how much of a nuisance still are naturally occurring sources of radiation?
So I have a story about this from snow days. So snow is, it's more important to be clean than Super K. So snow is, they're measuring solar neutrinos. I guess snow's not right, but snow plus, I guess it's the same problem. But yeah, on snow, we had one of our calibrations, we would look for something called the Berkeley blob. And this was, we think someone from Berkeley left a smudge of fingerprints on the acrylic dome, and it's kind of radioactive. So we were able to image that as a background and say, okay, there's the Berkeley blob. And so it matters that things are kept clean with these extra sources of radiation as a background.
Yeah, sorry, can I finish? So I work at an accelerator facility that has fixed target experiments, so we don't have to worry about being as clean. And I just wanted to say I admire neutrino physicists for sitting there and waiting and getting a neutrino a day or or something, when I can just turn on the beam and have gigahertz of rate. So billions, that's billions of events a second. So
I guess the follow-up to that is our beams are getting stronger. So at our near detector, we're going to have pile-up events. We might get 2 events per beam spin.
So probably the two of us can answer this. Yes. But when I went back in the mid-90s, when you were going in, so first you have to put on your overalls and hard hat to go into the cage and get claustrophobic with all the people pressing against you. And then you go through this tunnel, and not only do you wash off, you're suddenly told you have to strip down naked, go in a shower, and put on a white jumpsuit. Is it like that now?
Yeah, they just changed it to a blue suit now.
What's that?
They just changed it to a blue suit now. Yeah. Yeah, that is true. But I don't know, it's kind of fun because at least for the women's section, they actually have curtains in between, unlike the guys. So you have to actually strip naked if you're a guy in there and in front of everyone. But for us, we got lucky in a way, I guess. Another thing that we have, Snow Lab itself is very, very clean. If you're trying to transfer anything into the Snow Lab place itself, it has to go through the car wash, or that's what they call it. And they basically have a whole team that's just set on cleaning it constantly. And it's pretty cool. And you see people always walking around every floor. They're just somebody's always mopping. So it's kind of really cool. I think somebody said a stat that if you roll up all the dust that is at Snow Lab, you can just roll it up into a little ball that you can hold in your hand. And another thing that kind of reminds me, I think there is other issues with, if you're underground, yeah, you get rid of the background noise a lot, but you also get introduced to other stuff like radons. but I actually I can't really go too much into detail about it, but it was really cool seeing that there's specific parts at Snow Lab that are supposed to be like radon proof, which is really interesting to see. And that actually reminds me, I remember one time, there's like different like kind of cleaning sections at Snow Lab as well. So like in the lounge area, you don't have to wear like a hard hat, you can like sit there and eat lunch. And I remember it was like my first day and I pulled out a banana. And then one of my friends, or like he came up to me and said, "What are you doing? You can't have a banana here, you would like expose it to potassium." And I totally lost it. I thought it was like, I thought that was it for my career. But turns out he was just pulling my leg. So it was fine. I should have a little bit of potassium exposed, I guess, in the lounge.
So since neutrinos pass through our bodies like every second, do they contribute to the way our bodies work? And is it also like, does the rate vary how much passes through our body? So neutrinos don't interact very much, right? So Blair's the expert on that. But cosmic rays do, other particles are going through your body about 1 per centimeter squared per minute. So these cosmic rays are going through you all the time. And they're actually responsible for some mutation in cells and things like that. And so if you think about, now the word is slipping my mind. Evolution. One reason why evolution occurs is because there are cells that mutate. And cosmic rays are one source of that mutation. There's also Earth-based radiation sources and things like that. So it doesn't, neutrinos are a very small portion of that.
2 per lifetime, that's not going to have a big effect yet.
Right, so neutrinos themselves, no, but cosmic rays, yes.
We have another question at the back. Oh, sorry, yeah. Go ahead, sorry.
Yeah, pardon my French, but knowing that the neutrinos come from a decaying neutron, and we need supermassive detectors in order to detect the neutrinos, couldn't we have more neutrons decaying? And I suppose that is sort of something that's happening at the, what's it called? Where you produce electricity with splitting atom.
Right, so reactors, yeah. So reactors are definitely a large source of fission neutrinos. So that, from fission, you get a large number of neutrinos. And there are, so Super K and Snow Lab not really measuring those because it's the wrong energy range that they're built for. There's different detectors that measure, these are lower energy, there's a whole spectrum of energies of neutrinos, right? So solar neutrinos and reactor neutrinos are all kind of in the MeV, multi-big electron volt energies. And so at these energies, different detectors needed. You need to be able to see lower energy particles appear. So you need more light, so water churn conduction isn't used. You usually use something called a liquid scintillator detector. And so kind of the first neutrinos that were discovered were near a reactor, actually.
Thank you. Yeah, please go ahead.
Since neutrinos are electrically neutral, their masses is like orders of magnitudes less than that of an electron, and they are traveling at relativistic speeds. What do they interact with the equipment? Like, how do they do it? What to get detected?
We're getting into physics now. Okay, great. So in standard model of physics, there's sort of 4 known forces. There's the strong force, which is like what holds the nucleus together, the nuclear interactions that hold the nuclei together. There's electromagnetic, right? So this is light. Almost everything that we interact with is electromagnetic interaction. Gravity, we're being held down by gravity. And then the last one is called the weak force. This is responsible for beta decays and kind of all these decay kind of processes. So neutrinos can interact by the weak process only. It's called weak. It is less likely to happen. So it does happen, but it's just less likely.
Thank you. Do we have any other question? Oh, yeah, over there. Thank you.
So while I was watching the film, they talked about how there's a detector under rock in Canada, there's a detector under a mountain in Japan, I think it is, and then there's one under ice in Antarctica. What about space? Has that been considered as a location for a neutrino detector, or would there be other complications from the engineering perspective from that? I'm studying engineering currently, so.
I mean, yeah, I guess this comes back to my answer, how do you detect a neutrino? You need a huge volume of something that you're looking at. And so I guess the engineering challenge for space is, well, you need lots of stuff out in space. So it would be just too hard to get enough stuff up there that you could put your detector around.
There is a collaboration that is thinking about putting a detector in the Pacific Northwest, though, right, in the ocean. So instead of in ice, yeah.
Wherever there's a big volume of kind of free material that you can look at, it's good.
Thank you. I believe there was another question over here. Yeah, can you please give them mic?
I think we probably have time for like 1 or 2 more.
Yeah.
So my question was about getting to Snow Lab, because I've heard from a friend at the university that it's quite competitive, and I guess I was just wondering, was there anything that, maybe your supervisor mentioned that they saw on your CV that were like, we need to hire this person, or like, what do you think that you did different to kind of give yourself the edge?
Thank you. Yeah, it is very competitive. I think what I got, like in my aspect, I got really lucky is because what I was doing was this very specific niche that one of my my supervisor was looking for. So I worked at Moeller, and a big part that I did was I used an oscilloscope, and I was using oscilloscopes a lot, and I was doing it for testing on electronic bases. And that's what my supervisor was specifically looking for. So I think it was honestly just a very big factor in luck. But it also has to do with the fact that, I remember I was talking to him about getting in, and he said that for the most part, they also kind of look at people past first year. So it's very competitive because it's mainly first years that apply for it. So I think during that time, it was about like 200 plus students who applied for Snow Lab over the summer. It gets more competitive if you apply during the summer as well. And most of it were first year students. But I do think that, yeah, definitely getting to know and networking, because sometimes your supervisor could put in a good word. In my case, it was just strictly on making sure that I wrote my CV very well and kind of highlighting my specialty, but also saying that more or less I'm generally open to learning a lot of other things as well and aspects. And in an interview, I think I made a mistake, and I didn't really fall too hard on that. I just moved on, which I think people kind of immediately shut down when they make a mistake in an interview. So yeah, that's all I have. Oh, maybe also go for CAST, I'm pretty sure. It's like a summer school program that shows Snow Lab and also Queens and I think U of T as well. So I think it's also just like getting to go to that summer school and then maybe also applying again. It will kind of like really highlight that you're very interested and you've seen the kind of the standards that they have. Yeah, that's it.
Thank you.
Thank you. We probably have time for like 2 more questions, if anyone else wants to take the opportunity. If not, okay. Yes, no.
So my question was something about in the movie, they said that these detectors are able to detect these supernovas before we see their light. And so like I haven't taken any sort of like particle physics class yet. But so to me, like how can that be done if nothing can exceed the speed of light?
It's just the process that happens before. So, for example, let's see gamma ray burst, which is a really massive star that's going to explode. So yeah, this ultramassive star, and the core of the star is going to implode to become a black hole. But the outer part of the star still is an envelope that's going to explode while the inner part implodes. So what you have when it starts to implode, just before the explode, this is one of the ideas about it, is the black hole form jets. And the jets coming out, so you have magnetic fields and highly energized particles in the magnetic fields. As they plow through the material of the star, then they will create not only emission, but neutrinos or something like that. So before it becomes really bright, the neutrinos have been produced and ejected. Okay, so they're formed first and coming first. And then for this movie, it was a galaxy called NGC 1068. And the process is there for creating the neutrinos is that there's a couple of different processes, but they all relate to gas around a black hole. So the black hole has an accretion disk. The thing about the neutrinos is they're weakly interacting. So if there's a big dust donut around that region, they're going to go through it, and the light is not going to go through it. So the neutrinos are formed by, say, a star being pulled apart and forming an accretion disk around the black hole. And there's so many collisions, that the particle collisions, that neutrinos are formed. And then they're going to plow through the dusty torus or donut and come at us. And so we're going to see the neutrinos before we see anything else.
Cool, thank you very much.
I think Dr. Jamieson, did you also want to answer?
I think that was fine. I don't have anything to add to that.
Okay, yeah, we have one final question. Please, if you have any more questions, feel free to reach out to our experts. Like you heard, they have, like, their credentials are amazing. So yeah, please feel free afterwards. Let's hear.
So for gravitational waves, there's two facilities on one in each hemisphere to detect whether the gravitational wave was actually a gravitational wave or not, to confirm it. So do they do that for neutrinos as well, or do they know for a fact that yes, this was a neutrino?
So how do you detect a neutrino? So you don't actually detect the neutrino itself. What happens is the neutrino interacts with the nucleus or something, and you get out some charged particles from that interaction. Usually those match the flavor of the neutrino, right? So if it was an electron-like neutrino, you get an electron out, muon-like neutrino, you get a muon out, tau-like neutrino, you get a tau out. And so what you see in your detector is kind of just the spontaneous appearance of a particle, right? So you're looking for nothing, and then somewhere in the middle of the detector you get a track that looks like an electron track, or a track that looks like a muon track. So it tends to be very clear that it's either from some radioactive decay or it's from a neutrino interaction. So you do have to study your backgrounds very well to understand if it's from a neutrino or some other background.
Thank you very much. Please, you have